Okay, time number 8 of recording this particular video. We've been given, okay, we are discussing example problem 3.1 given in your textbook. So first of all, we've been given this particular chemical reaction, Mg solid plus 2Ag plus with a concentration of 0.0001 molar gives rise to Mg2 plus with a concentration of 0.130 molar plus 2 Ag, which is a solid. So we need to represent, there are two things, okay. First of all, we need to represent this particular reaction. We've also been given the E0 cell, which is equal to 3.17 volts. And we need to calculate the E cell. So there are two things we're going to be doing. First, we're going to represent this cell. And the second thing we'll be doing is calculating the E cell for this particular electrolytic process. So first of all, for an electrochemical cell, for us to represent it, it consists of three things: the electrode, the electrolyte, and the salt bridge. There are three things, right? The first one is the salt bridge, which is represented by these two lines. So the two lines represent the salt bridge. On the left hand side of this, you have the anode, and on the right hand side of this, you have the cathode. Okay, so you have the anode and the cathode. The anode is where the process of oxidation takes place, and the cathode is where the process of reduction takes place. Okay, so we are going to start with the oxidation half cell, then we'll have the salt bridge, and then we'll have the reduction half cell. So let's first write the oxidation and reduction half cells for this particular chemical reaction. So the two parts are magnesium, and if you find it difficult to predict if it's oxidation or reduction, first write down the half cells. You don't have to know if it's oxidation or reduction. So magnesium is giving rise to Mg2 plus. So obviously it has lost 2 electrons. So it's going to have plus 2 electrons over here. And the second one is the silver, Ag plus, which is the silver ion. It has an electron added to it to form a silver molecule. Or just to form silver, right? So these are the two half cells. So oxidation is where you have a loss of electron, right? So oxidation is where you have the loss of electron. So magnesium is undergoing oxidation, whereas the silver ion is undergoing reduction. So this particular reaction is going to be at the anode, whereas this one is going to be at the cathode. Right. So first let's write the representation of this particular cell. We will have magnesium, which is our, oh wow, that was bad. So we have magnesium, which is going to be the electrode, one line to represent the difference between electrode and the electrolyte. So Mg2 plus, and we can write it's a solid as well over there. And then here you'll have the concentration, which is 0.130 molar. And then you have two lines to represent the salt bridge. And then you have the ion, which is going to be the electrolyte, right? So Ag to Ag plus with the concentration of 0.0001 molar. And then one line to represent the electrode and the electrolyte and the electrode, which is Ag. It's a solid. So this is the representation of the, oh my God. This is the representation of this particular electrochemical process, right? Second thing we need to do is calculation of the E cell. Okay, so for this we will be using the Nernst equation. So if you know the Nernst equation, what we have is, according to Nernst equation, you have E cell equals to E naught cell minus RT by NF ln Q. So Q over here is nothing but the reaction. Basically, Q can be written as Q for a chemical reaction, AA plus BB gives rise to CC plus DD. For this particular chemical reaction, the value for Q, which I'm sure you learned in the chapter equilibrium, can be written as concentration of C to the power C, D to the power concentration D to the power D, A to the power A, and B to the power B. So this particular thing can again further be rewritten as E naught cell E minus, oh, let's go down a little bit. Okay. E naught cell minus 0 point, and basically, oh, I forgot to tell you, I'm sorry. This is the reaction quotient. So Q is the reaction quotient, and this particular thing can be rewritten as E naught cell minus RT by NF ln Q can be written as minus 0.059 divided by N log Q. Okay, and for our reaction, the value of Q for this particular reaction is going to be concentration of our, oh, so this is, oh, that's fancy. Okay, so this is our chemical reaction, right? So the reaction quotient for this particular reaction is going to be Q equals to the products, that is the concentration of Mg2 plus into Ag divided to the power 2 divided by the reactants, which is Ag plus square into Mg. And I have a video in detail explaining the reaction quotient. Feel free to check it out. So because we know these two are not ions, they can be ignored because they'll be equal to 1, and then basically this whole part of this can be ignored. So we can rewrite this particular we can write the equation for the E cell equation as, for this particular reaction, E naught cell minus 0.059 divided by N log concentration of Mg2 plus divided by concentration of Ag plus the whole square. Okay, so we know the value of N equals to 2 because you have 2 electrons, and we've been given the value of E naught cell, which is equal to 3.17 volts. Okay, so let's substitute those values and the concentration. So concentration of Mg2 plus, oh my gosh, equals to 0.130 molar. Concentration of Ag plus equals to 0.0001 molar. What I'm going to do is I'm going to rewrite this as 0.1 into 10 to the power minus 3. Okay, this is what we're going to be substituting in this equation. And I like showing you all the steps so you know where you know, basically. So you have 3.7 minus 0.059 divided by 2 log concentration of Mge2 plus is 0.130 divided by 0.1 into 10 to the power minus 3 whole square. Okay, so this we can rewrite. We are going to simplify in each step. 0.059 divided by 2 is 0.0295 log 0.130 divided by 0.01, because 0.1 whole square 0.1 square equals to 0.01 into 10 to the power minus 3 to the power 2 is going to be 10 to the power minus 6. Now this we can further write it as, so this whole thing will be equal to 10 to the power minus 8, right? Because you have these two, you switch this decimal point over to the right, you're going to get 1. So 10 to the power minus 8. This I just did so that it's easier to simplify. At least this is what made sense in my head. So basically, you get 3.17 volts minus 0.0295 log 0.130 divided by 10 to the power minus 8. Now, log A divided by, oh, and then 3.17 volts minus 0.0295 log 0.130 into 10 to the power 8, because we moving it from the denominator to the numerator. So this is equal to 3.17 volts minus 0.0295 log A by log into log B is equal to log A plus log B. So this will be equal to log of 0.130. I shouldn't have put it. Ooh, plus log 10 to the power 8. Right. So log 10 to the power 8. So we know log 10 to the 3.17 volts minus 0.0295. Log 0.130 is minus 0.886 plus log 8, 10 to the power 8 will be equal to 8. So let's simplify it further. 3.17V minus 0.0295 into 7.114. And this can be further simplified as 3.17 volts minus 0.209, which gives us 2.961 volts. So basically what we did in this particular question was we had to represent our electrolytic cell. We did that, excuse me, we did that by, just substituting it. We know what's on the anode, we had to figure out which was the oxidation and reduction of half cells, and then we used the Nernst equation to basically calculate the value of E cell. The reason we went through all of this is because I wanted it to be very clear for you, and for you to understand the various steps. So that we're done with example 3.1. Let me know if you want a video on the Nernst equation.